Hello, welcome. Let's try to solve another Leetcode problem. 510. Inorder successor in binary search tree 2. So this problem is the next problem of inorder successor in binary search tree 1, and this is going to be a little bit harder. Yeah, but what is the difference? So for this problem, we are giving a node. Yeah, so this is just a node. We are not only have the left and right node and value, but we also have the parent. So that is why, according to the question, we are just giving a random node. We are not giving the root of the tree. It means we cannot traverse the tree directly. We are just giving a random node, and this node can be any node inside the binary search tree. So this is the node structure. And what are we gonna return? So we're gonna return the inorder successor of that node in the binary search tree. So it's the same. For example, if it is not 1, so the inorder successor would be node 2 because 2 is here. Yeah. So if it is node 1, so the inorder successor would be node 2 because 2 gonna be the next value, next node whose value is greater than 1. So what is the next node of 2? It is 3. What is the next node of 3? There's no next node of 3, so it's going to be null. Yeah. Now let's check the next image. So for this example, let's just have a tag, and then I'm going to use the to method to solve it. Yeah. So for this image, the next node of 1 is 2, 2 is 3. So what about 3? It is 4. So this is one condition. Yeah, so one condition is just the node coming from the right side of my current node. So for example, if I were to calculate the next node of next successor of 3, definitely it's gonna be 4. So it can be at the right side of my current node. Yeah, so this is my current node. It can be at the right side of it. So this is one condition, at the right side. Yeah. So another condition is if there's no node 4, there's no this node. We only have a node 3. It can be the parent. Yeah, so it can be the parent of this node 5. So for example, and the second condition is that it can be the parent. Yeah. So these are the two conditions. But for node 6, what is the next node? It's gonna be the null. There's no next node. Yeah, even it has a parent, but we have to check if there's a value bigger than this 6. So for this 3, while we are checking the parent, there's a value 5 bigger than 3. So we're going to return this node 5 immediately. But what about the node 6? It has a parent, but there's no node bigger than 6. It is 5. And 5 has no parent. So it means for this node 6, if we were to find the parent, there's no parent. And also, for a node, for a random node, so for example, for this node 3, and which node we need to look first? Yeah, because for the parent we can find 5, but 5 is not the successor. The successor should be not 4. So this means for a random node, if there's a right child, we should always check the right child first, because it is a binary search tree. So if there's a left node at this place, I mean at the left side of this node 4, we should always choose this node. Yeah, maybe we can just use a random value. Maybe this is 3.5. I know all the nodes are integers, but if it is this node is just 3.5, so definitely we're gonna choose this node 3.5 because this is gonna be the successor of this node 3. So this means, first of all, we're gonna check the right node. If there's a right node of my current node, if there's a right child, if there's a right child, I'm gonna always find the left child of my current right child. It means if I can find the right child, I will always check the left side. And this left node gonna be my final result. Yeah, because even there is a right node, this node would always be bigger than this value and bigger than this node 4. Yeah, it means if I were to find a value bigger than 3, basically we're gonna first find the right child and then always go to the left to check. If there is one, if there is a left child, we're gonna return this one. If it still has a child, we're gonna find until to the last one of the left child. Yeah. so this is one condition. Another condition is we're gonna always find the parent. If we find a value immediately, if we find a value bigger than this node value 3, we're gonna return this node immediately. So there are only two conditions. We just need to check the two conditions. So first, we're gonna check the right child, and second, we're gonna check the parent. So this is just a solution which we can use the not dot value. And there's also another condition. So could you solve it without looking up any of the not value? Yeah. So I'm gonna explain the second solution later. So let's first focus on the first solution. So the first solution, as I explained earlier, first of all, but no matter, first of all, because we are giving the node, we can use this node immediately. Yeah, but how can we use this node? So yeah, let's just check this node. I'm gonna first find, so for a random node, for example node 2, I'm gonna first find the right child of this node, and then I'm gonna check if it has a left child or not. If it is, I'm gonna return this child until I find the last right child. Yeah, so this is gonna be my first way. So I'm gonna define a node. It's gonna be the right child. It's gonna be the not dot right. Yeah, so for example, my current node is 2. I'm gonna find a node 3. So right child is gonna be this node 3, and then I'm gonna check the left side. Yeah, and currently I'm not sure if I have a right child or not, so I have to check it. Yeah, because some node may not have a right child, so I have to check if while right child and right child dot left, if it has a left child, yeah. So this means my right child would equal to so this right child would equal to the not dot left, because it has a left child. Yeah, and if it has a left child, it will always go to the left child. Yeah, so currently this right child actually it's gonna be my first result. Yeah, now I'm gonna check it. Yeah, because I'm still not sure if this right child exists. Yeah, let me use an example to explain it. Yeah, still I'm gonna use this example. Maybe I have a node. It's gonna be 3.5. Yeah, how can I find this node 3.5? So currently this node 4, I'm gonna use the node 3 as my current child. So the not dot right would be this node 4. So while right child, it means this node and its left exists. So the right child would be equal to not dot left. It will be this node. And then while right child, it has no so this is a right child, it has no left, so it means I'm gonna return this right child. Yeah, but what if I don't have this right child? So if I check and check, yeah, it means it means the right child would be this node. So here, yeah, so here it's gonna be the right child dot left. So I'm gonna check this right child if it has a right child. So yeah, so if it has if this right child exists, I'm gonna return this right child. Currently I'm not sure if it is right, but this is gonna be the first way to find the right child, and then I'm gonna check the parent. So while not dot parent, this node would be equal to not dot parent. Yeah, so this is for checking a node. For example, this node 3, if it has a parent while not dot parent, so it means it is not 5, so this node would be shifted to not dot parent. Yeah, but I need to keep a value of this node because I'm gonna check it later. So I'm gonna use a reason as my reason node. So I'm gonna use a reason as this node. So I'm gonna check the value. Yeah, if not dot yeah, I'm gonna check it from here. If not dot parent parent and dot value is bigger than a reason dot value, so this means I'm gonna return the not dot parent. It means I've already I can find it. Otherwise, the node should be go to the not dot parent. Yeah. So if I cannot find it, I'm gonna return a noun. Yeah. So for example, for node 3, if not dot parent, if it has a parent, yeah, if a parent dot value, yeah, so while not parent, so I'm gonna check its parent. So for this node 3, if it has a parent, well, while it has a parent, so I'm gonna check it. If not dot parent dot value, this 5 is bigger than 3, so I'm gonna return this not dot parent immediately. So otherwise, so this node would be shifted to its parent. Yeah. So for example, for this node node 1, I'm gonna check its parent and find a value bigger than that. I'm gonna return a 2. And for this one, for node 6, so first of all, I'm gonna check its right child. It has no right child, so this means yeah, if right child, but for this node it has no right child, so I'm gonna return a noun. Yeah, but that now we can check the first 2 examples must work. Yeah, now I'm still need to check if this is right. Yeah, so I'm gonna check this. Yeah, still I'm gonna check this node, not 3.5. So currently the right child would be this node, not 4, and while right child this one and its left, so the right child would be equal to its left. It will go to this position, and then it's gonna stop because this 3.5 has no left. Yeah, so this is why we can return the right child immediately, whether it is a 4 or it's gonna be 3.5, but definitely it will be in this line. If this is not 4, it will be the last node in this line. Yeah. Now let me submit it to check. Yeah, maybe I need to submit it once more. Yeah, now let me submit it to check. Yeah, as you can see, it works. Yeah, so basically for this example, we just use yeah, we just solve it immediately. Maybe this time gonna be really fast, because for random node we just check from the top and from the bottom. Yeah, so from here it is from the bottom. We have to check from bottom first, because if it has a bottom for this 4, it must return this 4. Otherwise we're gonna find this 5. If we cannot find this node 5, we're gonna return a null. Yeah, and the second solution is that we can use this one. Could you solve it without looking up any of the nodes values? So we can solve it directly using the Inorder traversal. Yeah, because this is similar like the 285. We're gonna just use a traversal and find it. Yeah, let me just copy the code. Yeah, because it's not gonna be very similar. Yeah. So the only difference is that so this is just an Inorder traversal. we're gonna put all the nodes inside a result array, and this is to check which node gonna be our final answer. Yeah, because if we use Inorder traversal for the node 1, 2, 3, it's gonna be like this. Yeah. If we want to calculate the next node of node 1, successor of node 1, it's gonna be the next one. So this is why we're gonna return result I plus 1. Otherwise, we're gonna return none. And we're gonna check from n minus 1 node. Yeah, so we're gonna check this node 1 and 2 to calculate the next. Otherwise, we're gonna return none. Yeah, but the difficult from this problem is that we are not giving the root node, but we are giving this parent. So this means we can find the root node. Yeah, so we can use while node dot parent exists. So our node would be equal to the node dot parent. Yeah, so for example, if this node 1 has a parent, so the node would be equal to this node 2, and then node 2 doesn't have a parent, and then we're gonna get this node. So currently this node is the root node. So we're gonna put it inside DFS with this node, and then we get an empty array, and then we put all the nodes inside an empty array in increasing order. If we find one, we're gonna return it. Yeah. Now let me run it. Yeah, I need to check some variables if this is equal to the node. So here I'm gonna use a variable, maybe a temporary variable, maybe p should equal to node. Yeah, let me use this node p. So while p have a parent, so p should equal to p dot parent, and then I'm gonna put p inside. Yeah, because I don't want to because I want to use this node later, so I will give a temporary variable p to check the parent. Now p is the parent, I'm gonna put the parent inside, I'm gonna put the root inside to get the array, and finally I'm gonna check if it is equal to my original node. If it is equal, I'm gonna return the result. Yeah, as you can see, it works. Now let me submit it. Yeah, as you can see, it also works. Yeah, maybe I think the second solution may be easier. Could you solve it without looking up table? So without looking up table, it means we will not use the not dot value. So for this one, we didn't use the not value. As you can see, this is gonna be easier than the iterative solution, because this is a recursive solution, and the time complexity and the space complexity is both O(n). Thank you for watching. See you next time.